you're good. Okay, fine, folks. As I said to you yesterday via Remind, I will try to remind you to pay me the $10 ASAP, but I put that on my Visa. All of it on my Visa. And my Visa auto pays, which is bad, okay? Because I have to have the cash before I auto pay it. Number two, I am hoping that you can continue with your note 6. You can finish the notes. I highly suggest you look over my solutions and you finish the notes, because then the Webassign is based on those notes, okay? So I think we're ready to mentally move on, though, to note 7, which is a little bit more shorter and sweet. And this just kind of sets the tone for what we're going to be doing as we finish up our unit. And I don't know how long it's going to take. And we will have a test at some point before Christmas. And all I'll tell you is that it's going to be the last week before Christmas. And I'll make sure it does not overlap, at least the Calc BC test, which is what? You said Tuesday, Wednesday? Monday, Tuesday. Okay. All right. Sounds good. Okay, here goes. What this side of the paper is I'm just trying to show you that I honestly don't know my rotational equations. And I could not even do number 1 right now, calculate the work done, because I don't even know what that is. But what I do is I do know all of my last year's equations. And because I know those, I can make quick analogies and I can come up with the rotational ones within about, 2 seconds. And so that's what I'd like you to be able to do, so that you don't have to add a whole bunch of new equations to your repertoire. You will find out that these equations are not on the AP sheet, so you have to know them. So learning them from last year, I think, is going to be easiest. All right, so here we go. Last year, do you remember what the equation for constant velocity is? D divided by T. All right, so then you say, well, then what would it be if I was talking about a merry-go-round going at constant velocity? So that would be omega is theta over time. So I make the quick comparison. The acceleration equations, I did my colors wrong. I was supposed to do that one in green, so I'm just going to flip them. My acceleration equations are normally orange, now they're going to be green. So do you now know your equations from last year? No?
Oh, AT.
AT, yeah. D equals? Do you know that one? Do you know VF squared equals?
Initial velocity times.
This is initial velocity times time plus 1/2 AC squared. Now, I will admit that those are on the AP equation sheet, but we already looked at them one time. They're not written very clearly, but you could probably decipher and get that out of what they have written. And because of that, can you make the quick comparisons over here, which we've been using these, so I bet you can do these fairly quickly. So all of my A's become alphas. Okay, and where we have been right now is we have been using Newton's second law. I'm going to write that as F net equals MA. And then we can make the replacement, but instead of talking about forces, we care about torques. Because torques have a force in it. And we don't care about mass, we care more about the distribution of mass. And the distribution of mass is hidden in an I equation. If the mass is far away, it's going to go slow. If the mass is closer to the axis of rotation, it's going to go fast. And alpha becomes T squared. Okay, so do you remember what the equation for work is from last year? FD. Work is FD. So now what do you think work is on this side? Instead of F's, what do we talk about? Torques. And instead of D's, we have thetas. All right, but I want to remind you that a torque is an FR. A torque has an F in it. So I'm going to break that down to FR theta. Torques are FRs, so not just a plain old T. All right, do you remember what power was?
2.
That is true if we're in circuits, but power is how fast you do work. So work over time. I wish I would have wrote this further to the left. So bear with me as I squish this in. And force, or work, is force times distance over time. And I purposely put the T just under the D, because then power could also be force times velocity. So now I'm going to do that same thing over here. Power is work over time. But if it's a merry-go-round rotating, the work is going to be torque over time. And if I put the T just under the theta, remember theta over time is a W? So then I could say, oh, then that would be torque times W. But remember that a torque is an FR, so it really would turn out to be like FR times W. So again, I don't memorize that, I just like work it out. Say that again. What's your question?
Oh, no, it's Sydney's mom's birthday, so I was trying to meet her to her happy birthday.
Oh, well, that's good. Sydney's mom, happy birthday, Sydney's mom. On our video. Please let your mom listen. Yeah. Okay. Tune in. Okay. Okay. So, gravitational potential energy is the potential energy when we have something up high. So I'm just gonna draw a cliff with the bowling ball on top of the cliff, and we would call that PE, which now we've kind of switched to the variable UG, but either one equals MGH. We also have gravitational potential energy, even if something is, well, if something is kind of rotating. But I'm just going to write it differently over here. I'm going to write PE equals UG equals MGH, and I'm going to put a little CM there. Remember what CM stands for? Center of mass. Center of mass. All right, we're going to use that today. You'll see what that means. All right. I want to just cross this out. I was going to recopy the worksheets, and I felt guilty about like throwing them away just because I goofed. All right, the next one is kinetic energy. Kinetic energy would be, kinetic energy is 1/2 mv squared. So what do you think the kinetic energy for a merry-go-round is? Okay, 1/2. But we don't care about m's, we care about the distribution of mass. So that's got to be an I. What do I mean by that? It means if I was on a merry-go-round, so it would be the mass of the merry-go-round, and let's say I was standing on the merry-go-round. I care about where I'm standing. Am I standing on the outside of the merry-go-round? Am I standing near the middle of the merry-go-round? Because I could affect the kinetic energy of the merry-go-round. And obviously the V is going to turn into a W. So 1/2 I W squared. All right, kinetic or conservation of energy. I'm going to write way over here so I have space. I'm going to write ET equals the potential plus the kinetic. So the potential is going to be MGH plus the kinetic, that's going to be 1/2 mv squared. Technically, It's the ET at spot 1 equals the ET at spot 2. So it's mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared. And we go from there. All right, but if I'm rotating, and we're going to go into this more detail on Monday, so I'm just going to skip it today. But if I'm rotating, I have the old kind of kinetic energy happening. Let me rephrase that. Picture a car tire. So the car tire is rotating, but the car is traveling down the street. So we could talk about the rotation of the tire, or I could draw the tire as a dot and say the dot's going from point A to point B. So this is the old stuff, but now I got to put on the rotating wheel. So this expands. We're going to end up with two kinds of kinetic energy. So this is going to be ET equals mgh plus the old kind of kinetic energy, 1/2 mv squared, plus the rotating wheel, 1/2 iw squared. And so it's going to expand. Now, sometimes we will cross out one of those things, but I need to think of conservation of energy in that way. But this whole purple thing is Monday's lesson, so we won't worry about it too much today. All right, there is another way to find work instead of FD. And people always forget this one, and that's why the AP people love this one. So work is also equal to the change in kinetic energy. Let me say that in casual language. You're driving your car 40 miles an hour, and then you speed up to 60 miles an hour. Your engine did work because your engine changed the velocity or changed the kinetic energy of your car. And so to find the work, I'll write it out. It's always the kinetic energy final minus the kinetic energy initial. So that'd be like 1/2 mv squared final minus 1/2 mv squared initial. So if I change the velocity of something, work was done. So I have the same kinetic energy theorem over here. Work equals the change in kinetic energy. And to save ourselves the writing, it's still going to be kinetic energy final minus kinetic energy initial, but this time it'll be equal to 1/2 iw squared final minus 1/2 iw squared initial. I don't know about you, but I remember when I was in college, I could never remember if it was final minus initial or initial minus final, and it matters. Anyways, I just memorized for myself. They're in alphabetical order. So final comes before initial. All right, do you remember from last year what the equation for impulse is? Impulse. Do you remember what the variable for impulse is? No, that's all right. So impulse, you want to say I, but it's not I because that's rotational inertia. So they didn't use I, they used J. 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 And impulse, let me give you an example of impulse. We talked about, I'm going to write it down, it's FT, but here's my example, FT. We talked about trading force for time. Impulse is I'm going to crash into the tree, but if I can make myself crash into the tree for a longer time, then I'll have less force acting on me. So I wear my seatbelt. I have an airbag. I purposely drive through a snowbank on the way to the tree. All that is increasing the time of my collision. All right, now we have to replace it. What would impulse be over here? What would you replace the F with? Torque. Yeah, torque and then time. TT. But remember that torque is an FR. So FR in a T. Jack, I think what you were remembering was momentum. That's rho. What's the equation from momentum? MV. MV. This is an anomaly. They don't use P now. We changed the variable to L. That's like the only one we changed the variable for. Instead of M, what do we care about? The distribution of mass. And our V becomes a W. And then last year, we had the impulse momentum equation is when you like hook it all together. So I'm going to hook it together. I'm going to take the FT and hook it to the MV. But I'm going to write it this way. FT equals M. So if I apply an impulse to a mass, I will change its velocity. If I apply a torque on a merry-go-round, I will change the rate at which it's spinning or rotating. All right, so what do we have to do yet? So today, we're going to be talking about, I'll call it the pink stuff. Monday, we're going to do the purple stuff. And that'll be like Monday and Tuesday. And then we'll probably finish up with end of next week with the green stuff. And then we got to do the AP multiple choice, AP free response, and then we'll be ready for our test. All right, today we're going to focus on the blue stuff. So we're flipping. We're going to do 3 examples. So I got to do them in 10 minutes or less. All right, so here we go. All right, a 50-kilogram merry-go-round. Whisper so I don't hear you. 50-kilogram merry-go-round with a radius of 4.5 meters is rotating at 2 radians per second. A physics student brings the wheel to rest in 4.5 seconds. So this merry-go-round is going around, and somebody walks up to it and grabs it and brings it to rest. What you're supposed to realize when it says calculate the work done, so you might, this is what goes through my head. Literally goes through my head. Well, work is force times distance. Oh yeah, but it's a merry-go-round, so it'd be torque times this, and torque is an FR times this. And I will say, I don't know any of that stuff. I don't know the force, I don't know the theta. Dead end. And then I remember that if I hit a dead end, that maybe I should remember the work kinetic energy theorem. Did I change the velocity of the merry-go-round? Yeah, it was going 2 radians per second, and the student brought it to rest. So then I'll write down 1/2 I W squared minus 1/2 I W squared. All right, so let's look at the work. What is the final velocity at the end of the story? 0. So I'm going to X that out. So do you see how my answer is going to be negative? Work can be negative, and that negative sign is meaningful. So we have to have that negative there. All right, since the student is stopping it, it's going to be equal to 1/2. What would be the I of a merry-go-round? How about a 1/2 MV squared? M would be 50. Oh no, 1/2 M R squared, right? M R squared. R is 2.5 squared. 1/2 MV, 1/2 M R squared. And then initial velocity is 4 radians per second. 2, I'm thinking 4. And then I number crunch all that. Blah, 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 blah. And you know what? I just did it during lunch. 312.5 joules. So somebody stopped the merry-go-round and they spent this many joules. I should write in the I, 1/2 mr squared. Did it work? Are we good? All right, the next thing, determine the power. The power dissipated is kind of like a physics vocab word. It means spent. Find the power spent. And all you need to know for power is that power is work over time. And since I already have the work, so somebody might say, why did I drop the negative sign? We really can't have negative power because power is what you spend. And that's what the negative sign means. I spent it. So there's no need to have it there. And we did this in a time of 4.5 seconds. And when I have joules per second, that will turn out to be watts. Yeah, there's a lot of W's. W is a unit, W is a variable. Yes.
So the AP test, we wouldn't need to bring the negative back.
We would not bring the negative back, right? Because power is what you spend. Power is what you spend. But work can be positive. It's positive if you speed something up, and it's negative if you slow something down. Okay. All right, the next one. I edited this, and I forgot to cross out the apostrophe and the S. So I have 2 edits I got to make on this worksheet. All right, what is the kinetic energy of the Earth as it rotates about wow, its axis? What is the kinetic energy of the Earth? Joules are tiny, so there's a lot of joules of kinetic energy. But how do we figure out the kinetic energy of the Earth? Well, there's like this axis of rotation here. So the Earth is a ball, a sphere, spinning about its axis through the center. So I don't have to parallel axis theorem anything. So it's going to be kinetic energy equals 1/2 IW squared. My new equation for kinetic energy. So 1/2 I. What would be the I of the Earth? Yeah, I is going to be 2/5 mr squared. So what's that going to be? 2/5 5.98 to the 24. On the AP exam, just FYI, they usually don't make you memorize that number. They usually give it to you, and they often use a 6 instead of a 5.98. But we're smarter than that. 2/5 mr squared. What's the radius of the Earth?
6.64.
6.38 or 6.4. 6.38 times 10 to the 6. But I got to square that. And now, W. What's W? 1 rad a day. Wow, that'd be really nice if it was 1 rad a day, but you just made that up. All right, so what does the Earth do? It makes 1 rev. No.
Nope.
It makes 1 rotation a day. All right, but what do I have to turn this into? Radians per second. So 1 rev. One spin a day. Okay. So 1 revolution a day. 1 rev is 2 pi radians a day is 24 hours. 1 hour is 3,600 seconds. That's gonna be a big number. well, no, it's gonna be a small number. It's gonna be a small number. 40727? Are we trusting you? 4 zeros. 1, 2, 3, 4, 7, 2, 7. All right. 2 times 5. 4 zeros. All right, and then it's W squared this. We gotta square that number. 1, 2, 3, 4, 7, 2, 7 squared. All right, and if I number crunch all that, we should get that answer. Okay, let's look at the last one. The last one, this one, is the most important one. All right, so stick with me on this one. This one can be a little confusing. So I'm going to use this. All right, number 3. It says a 2.2 meter thin rod is held vertically with one end on the floor and is then allowed to fall. So what that means is this. I gotta create myself a little bit of space. So I call it something tipping over. So I'm just gonna hold it at the bottom. This is what's happening. Here goes. This is the rotational analog of the bowling ball falling off the cliff. So I have something tall and it's rotating. So I'm going to go back to this where I drew the gravitational potential energy. Over here, I have something tall. I'm going to put a pivot point here and I'm going to allow it to fall. So you can see that here potential energy turned into kinetic energy, but here potential energy turned into rotational kinetic energy. All right, so first of all, you have to recognize when this is applicable. I have something tall and it's going to fall over. So to tell myself that it's going to fall over, I'm going to draw the stick falling over like this. And I'm going to go like this. I drew my stick a little too long. All right, so I have potential energy. Guys, I'm okay with you talking, especially if you're discussing things, but it's actually very distracting. So you just got to do it quiet enough that I don't hear you. All right, I'm doing conservation of energy. The kinetic energy or the potential energy is going to turn into kinetic. Or you could think about it this way. It's however your mind thinks. I'll talk through it the second way if your mind thinks that way. At the start of the story, the stick is standing up. The second part of the story, the stick is falling down, and this would be like right before it hits the ground. Kind of like the bowling ball at the top of the cliff, and then right before the bowling ball hits the ground, what would be its velocity? So you could talk about the stick, and you could say, does the stick have potential energy? Yes, I'll come back to that. Does the stick, when it's standing up, have kinetic energy? No. All right. Why does the stick have potential energy? When it's the bowling ball at the top of the cliff, the bowling ball was a dot, and I could see that it had potential energy. But what if you had to take this stick and collapse it into a dot? Where would you put the center of mass of the stick? Where would you put the dot? In the middle? Does that make sense? So that's what we're doing. We're mentally collapsing the whole stick, and the dot goes in the middle. So I'm going to put a little dot right here, and I'm going to label it center of mass. Because I have to collapse that, and so now the potential energy is mgh, but the h is the center of mass. So I don't know the mass of the stick. I do know 9.8. And I do know what the center of mass would be, because if the stick is 2.2 tall, the center of mass would be 1.1. So you have to collapse the object and turn it into a dot, and the dot does have potential energy. Now it's going to fall. When it falls, it's going to turn into, all right, so here goes, falls. When it falls, it's now on the ground, so I don't have any potential energy. And so we can see that the potential is going to turn into kinetic, but not kinetic energy that drives the cart on the street. Rotational kinetic energy. It's going to make a rotation. It's making a quarter of a turn here. So I'm going to use the rotational kinetic energy. 1 half I W squared. It'll make more sense as I keep going here, but I'm going to solve for W. So that's going to equal 1 half. What's the I of a stick about its end? About its end. 1/3. Okay, a stick about its center is 1/12, but then you have to parallel axis theorem it down here, but we already know it's 1/3 ml squared. Are you with me? 1/3 ml squared? All right, so I'm going to just pencil that in. 1/3 ml squared. All right, so 1/3, I don't know m. L is the length of the entire stick. So that's 2.2 squared. And then I have W squared. And that's actually what I'm solving for. I'll explain why I'm solving for that here in a minute. But, all right, what do we got going on here? Do you see how the m's cancel out? They don't matter. Will you take a minute and would you find W? Because I don't have that. We need that. Those are not the answers that are on the paper. We need W. I don't know if I did that. Oh, I did. I got 3.66. Someone else get that? Okay. So, as it's falling, this is how fast it's falling. W equals 3.66. That would be like if it was a merry-go-round, how fast the merry-go-round would be going around. That's how fast it's falling. But those weren't the questions. Letter A, find the speed, that means velocity, of the other end of the stick when it hits the floor. So you could be standing anywhere here. If you're standing farthest away, you're going to get hit with the greatest velocity. This person gets hit the most. Watch. All right, what would that person's velocity be when you're standing far away? So if you were standing at the end of the stick, where the end of the stick hits, the velocity would be 2.2 times 3.68. Does my phone ring every day? Yes, it does. Okay, and you would get hit with, when you multiply this out, that should be the 8.04. So I'm going to write that right here. 8.04 velocity equals. But what if you were only standing halfway? That's the second question. Find the speed and the velocity of the center of mass of the rod when it hits the floor. So when the center of mass hits the floor like this, it's still rotating at the same W, But obviously the velocity, when I do RW, this is only going to be a 1.1 times 3.66. And I get hit with a velocity of 4.03 when I'm here in the middle. And obviously I could calculate the velocity at any spot along the way once I know how fast it's rotating as it falls. All right, this is a classic AP question. So we're going to circle that one because that's going to for sure be on our next test. For sure, for sure. Okay, let's stop there. There is a Webassign that goes along with this lesson, and you still have your old Webassign floating out there, right? Did I set that for Sunday?
Yeah.
Yeah. I'm going to look at this one. If I think it's short and sweet, I'll set it for Sunday. If you need an extra day, I'll put it for Monday, okay?